All right, good morning or good day whenever you're watching this. Today we're going to talk about stars. And I'm going to be flipping back and forth between a fill out version of the notes and the notes on the PowerPoint just because there's some really cool images that I think will drive home some of the points. But just as some fun facts, I don't believe you have to write these down. No. Stars were the first guides for navigation. If you think about Moana, if you watch that movie, you know that before there were any other like GPS, maybe even maps, like stars were the way to figure out where you were going and where you were. So that's kind of cool. If you haven't seen Moana, hit that up. Anyway, the closest star to Earth is the sun. That's a question that you might want to write down somewhere just because I've seen it on tests every now and again where it's trying to trick you, where it's like, oh, there are billions of stars in our solar system. And kids usually think like, oh yeah, our galaxy has so many stars in it, tons and tons of stars. True. But the key word is solar system. So in our solar system, there's only one star, and that's the sun. Okay, moving on to our notes. So stars are a large, hot, glowing ball of gas that is powered by nuclear fusion. And there are 9,000 stars visible to the naked eye. And this image here is showing you, if you're in the inner city, you really can't see any stars. There's too much light pollution. Suburban or urban, I don't know what that says. It's in the middle between the inner city and the suburban sky. That I feel like I live in the suburbs. I have a sidewalk. Each house has like a little lamppost at the end so that it looks like all magical and like Narnia if you go outside at night. Anyway, it's with those lights, that's going to block out some of the light coming from the sky. You can't see the stars very well. Rural sky, if you guys are in more of a rural area of our school district, this is how many stars you would be able to see. And then if you go to something like a dark park, that up in northern PA, I think it's like Cherry Creek Park. That's a dark park, which means there's no lights allowed within the park. If you do have like any kind of flashlight, you have to turn it on like the red mode. I don't know if you've ever used one of those like to go caving, or it's a flashlight that you strap to your head and there's a light on it and you can flip it to red mode, and that is mandatory. You cannot have any like bright lights in the dark park. And the reason that is because they want you to be able to experience actually seeing the Milky Way, because you can see this line of stars where that's the edge of our galaxy. It's really, really cool. So anyway, you obviously should take note of that definition. So let's highlight that. A large glowing ball of gas that is powered by nuclear fusion. All right. When it comes to our Milky Way, though, there's approximately 200 billion stars, so tons and tons of stars. The second closest star to us is Proxima Centauri at 24 trillion miles. So this is what our Milky Way looks like if we could stand back away from it and really see what it looks like. Remember, the middle is a black hole. Space is always trying to kill you. But we're luckily out here in one of the arms, so it'll take a while for us to get kind of sucked in there, which is nice. But anyway, our second closest star is Proxima Centauri at 24 trillion miles away, or 4.2 light years. So if you were traveling at the speed of light, which remember, in 1 second, light can travel around the Earth 7 times. That's how fast it's going. It would still take you 4 years. So the closest star is very, very, very far away. Space is big. It's very big. So we use a measurement called light year. Remember, it's 6 trillion miles, the distance light can travel in 1 year. Okay. And you had written that down before, but I think it's worth highlighting that and saying this is important. Okay. So just as a heads up. Now, when we get to how to classify stars, all right, it's related to the stars. Characteristics of the star are related to a star's stage of life and mass. That is super, 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 super important. It's like super important. Highlight that. Okay. And color is the first thing that can kind of break stars down. You'll see right here, here's a little chart. There's blue, white, red, or yellow, orange, and red. So there's no like green or purple stars, but it goes pretty much Roy G. Biv. So red, orange, red is the coolest. Remember, it has the least amount of energy, the longest wavelength. Red, orange, yellow, white, blue, and like super dark blue. Okay, so let's take note. We determine the color by its temperature. It's called a spectral class. So the cooler stars are going to be red, the hottest stars are going to be blue. And if you're like, wait a minute, in art class we always colored cool colors blue and hot colors red and orange and that kind of stuff. Well, in science, it's actually the opposite, okay? So you think about, you all have used Bunsen burners, hopefully, unless last year with COVID, you didn't get to that part of the unit. But for a Bunsen burner, let's do this, Bunsen burner. Okay, this image right here is showing you the hottest part. They always said, make sure you use the blue cone. You want to see this blue part right here. That is the hottest part of the flame, okay? So in science, it's kind of the opposite. Blue is the hottest, which makes sense because remember, that part of the spectrum has like a higher energy level. Okay, blue does, whereas red is a lower energy level. I don't know how it got flipped for art, but in science, blue is hottest and red is cooler. Okay, now that's not saying like if you go over here 3,000 Kelvin, you're still gonna burn your face off. If you go and you're like, oh yeah, let me touch this red star, like dumb. You will burn up, but it will not incinerate you. You could get a lot closer than over here where you would just like, okay. All right. I digress. Whoa. All right. So you definitely need to know this. This will be on your test. The hottest is blue. Then it cools down to white, cools down to yellow, orange, and red is the coolest. All right. The size of the star is another thing. Ooh. Oh, wait a minute. This is a diagram that helps organize stars that they observed in space. Red is over here. You can see there's some big red ones, there's some little red ones. Either way, they're cool. Here they get a little warmer, and then here are your super hot ones. Okay, so this is the spectral class, and they have a whole different level of like there's letters that are assigned to it, but we don't need to know that. We just need to know red, cold, blue, hot. Okay. The next thing is the star's size, and that depends on the starting mass of the nebula. So how big the nebula is, remember, a nebula is gas and dust that will start clumping together to make a star. And if it's a big nebula with lots of gas and lots of dust, that's going to make a big star. Whereas a little nebula is just going to make a little star. Okay, so it depends on the starting mass of a nebula. Let's highlight that. And it ranges from supergiant to, fix that in your notes, giant to average to dwarf. So they're very small. I'm going to play part of this video right here, maybe. Yeah, so come on now. All right, and it's going to go through. There's Mercury. There's Ganymede. That's a moon of, I believe, Jupiter. There's Mars. Here's Venus. Earth is right next to Venus. They're called sister planets because they're about the same size. And then this is like a small sun, Kepler-10. It's a dwarf star. Still pretty big. And I'm not going to show you all of this because I'm running out of time. But while you look, so there's Jupiter. There's another dwarf star. But the sun is super, super small. I think it's this guy right here. This is a star that is much, much larger. This is, I think, the largest planet we've observed ever. And then right here is our sun. Now, it's going to get a lot bigger. I wish I could speed this up. Can I make this faster? What you're going to notice is they just keep getting bigger and bigger and bigger. They get huge. Just keep on getting. That's an orange giant, so it's pretty cool. This is a blue supergiant. That's a blue hypergiant. So they just keep getting bigger. I feel like you guys get the drift. Anywho, so that's the range, and we're going to talk a little more about those later. The brightness depends on the size and the temperature. Okay, so let's highlight that. And there's two different ways that we look at brightness. Okay, there is the apparent magnitude, which is the brightness as seen from Earth, and distance is a factor. Just like a car coming at you, if you see a car off in the distance, the light isn't going to be as bright as if there's a car like right up on you and the lights are on, it's going to be super bright. So apparent magnitude is how bright it appears from where you're at. Absolute magnitude is the actual brightness of all stars if they were the same distance from Earth. So if we bring all the stars in line with the sun, it's the absolute, it's like, hey, this is actually how bright these stars are. This one's brighter than this one. This one's brighter than this one. So more often than not, we use this, or scientists use this. This is what we're seeing at night. Okay, the brightest star that we see, BT dubs, is the sun because it's right next to us. Okay, I'm going to pause there, and there will be a second video later going over the formation that you'll probably have to watch today. Okay, have a great day. Wait, let me make sure that this is, yeah, we'll move on to the next part in another video.